Hi there, I am Alperen. I'll be presenting my work done within the scope of my graduation project. In this project, I have designed a broadband dielectric resonator antenna, which is also abbreviated as DRA, based on silicone elastomer material. First of all, I have begun with performing a literature survey about the DRAs. They use a resonator made of a dielectric material to radiate. They are famous with their high radiation efficiency, low conduction losses, compact size, and wide bandwidth. The antenna was first proposed in 1939. They have lots of attractive features as given here. And also they have various shapes to be chosen, like cylindrical, spherical, and rectangular. I have preferred working on rectangular DRAs because they offer practical advantages over cylindrical and spherical shapes. The mode degeneracy can be avoided in the case of rectangular DRAs by properly choosing all dimensions of the resonator. For a given resonant frequency, two aspect ratios of a rectangular DRA can be chosen independently. The bandwidth of the RDRA also depends on its aspect ratios, so it's actually more flexible and easier to have a bandwidth control than the other shapes. Here, in the right figure, different DRA structures in the literature is given. Here I will be talking about my design constraints. First of all, DRA dimensions are proportional to the free space wavelength over square root of the epsilon r of the dielectric resonator. In the literature, many of the designs have high dielectric constants like 20 and higher, and higher frequencies of up to 20 or maybe higher gigahertz of frequencies. So it's actually easy to obtain low profile DRAs in those type of designs. However, in my project, it's not the case here. My resonance frequency is medical ISM band, and my epsilon r is just 2.5. The array dimensions are actually determined by considering them as a truncated waveguides. So in this regard, the electric waveguide model had been created and used for the DRA designs to determine their dimensions. DRM considers isolated DRA in free space like this. Also, fundamental modes of the rectangular DRAs are TA01 delta, which delta refers to the truncation of the waveguide, and hybrid electromagnetic waves. Here are the dielectric waveguide model equations for TAMN modes. First of all, Kx and Ky must be found. Then second equation must be solved and Kz must be determined. There is also a transcendental equation for the wave number Kz given in the third equation like this. Finally, for given the DRA parameters, DRA dimensions are the ones where Kz calculated by the first two equations here also satisfy the third equation. The design should be as broadband as possible. Also, the bandwidth of the DRA increases with the decrease in width and the height of the DR. So these two must be kept as small as possible. Since the fundamental mode of the DRA is TA01 delta, width can be varied easily because Kx is simply 0. So it means that it actually does not have so much impact as the other two dimensions do on the resonance frequency. So simply I just did not include the height in the DMM equations and related it with the other parameters to determine the width height value, which also satisfies the DMM equations and the broadband constraint. Height in terms of DVM parameters in this regard is just like this. DMM equations are not easy to solve on paper, so I programmed on MATLAB to solve them, given in the left figure. This code first calculates the equation 1, equation 2, and equation 4 to determine a height for a wide bandwidth. Then, this height value is substituted in equation 3 and whether equation 3 satisfies is checked. If it's satisfied, then the theoretical background is completed. The solution ended up with a large length of 15 centimeters. As far as the third reference is concerned, the dimension can be halved. Cool that the dimensions of length and height shall be kept as small as possible, as I just mentioned. However, lowering B results with extreme increase in height to satisfy the waveguide model equations. So in the final stage, I have just considered the resonator dimensions like this. I have given here two figures. Upper figure shows the most common type of design of the dielectric resonators. To obtain a broadband DRA excited by a microstrip line, I have cited the third reference, which is a quite different type of design. Differences are just like this. Materials in my design are given here. To obtain better bandwidth performance, I have optimized the height value to be approximate around 2.4 centimeters rather than the one that I found in the theory. The design results, like S parameter and 3D realized gain plot, are as follows. The DRA has a 10 dB bandwidth of approximately 235 MHz. It just resonates at the center of the medical ISM band, a good radiation pattern I have obtained, and it just radiates like a magnetic dipole. Here is the 2D radiation pattern. In theta equals to 0, it has a omnidirectional radiation pattern, and here it's just like this. Dimensions determined in the DFM solution section are further optimized to obtain better performance of bandwidth and low profile. So the final dimensions I have obtained and the results I have shown has dimensions like this. The most important result is that the array is quite low profile as compared to the operation of wavelength, almost 1/3 of a meter. Here are my references for the information I have provided in the presentation, among which I have also used for my project. Thank you for paying attention and listening to my presentation.